So everything that we've done so far was for a first order differential equation. And so when you run into a first order differential equation, you should be able to tackle it using some of the techniques that we've had. Chapter 4 begins with higher order differential equations, and we'll end up focusing on second order differential equations, but we're going to get introduced in the beginning to just general high order differential equations. And so I want us to get used to the notation that we're going to be using. And this isn't much different than what we've seen before, except now, since we have higher order differential equations and we don't know how high the order goes, that'll just get represented by the nth order differential equation, which means if we don't know what n is, then we use these symbols and subscripts and dots and all that stuff. So we have a differential equation written this way, where we have some function of x times the nth derivative of y, and then another function of x times the n minus first derivative of y, until you get just to the first derivative and then y itself. That's a notation that I'm talking about that could get kind of complicated. The subscript notation with the n minus 1, and it goes down to just the first derivative, and the zero, technically this is a zeroth derivative. If y is the function, the first derivative is y prime, the zeroth derivative is back to itself, y. So what they're saying is that if we have an nth order differential equation and you have a corresponding n initial conditions, that's what this is saying. This is your initial condition for the original function, for the derivative, and for the n minus first derivative. Then this whole package is an initial value problem, an IVP. So that's the introduction part. And this very first section starts off with a big theorem that says that if you have some certain conditions satisfied over some interval that contains some initial value, then you're guaranteed to have a solution. So that's the existence part. There exists a solution. You're guaranteed a solution. But beyond that, you're not only guaranteed a solution, but if you find your solution, then that's the only solution that exists. And that's the uniqueness part. So this whole idea of the existence and uniqueness is a big theoretical part of differential equations, where you can ask yourself, when can I guarantee that I'm definitely going to have a solution? And how can I guarantee that my solution is going to be the only solution that exists? All right, so what are the conditions for the existence and uniqueness theorem? The conditions are that each of these functions of x, including the right-hand side function, are all continuous. No zeros in the denominators and negatives under square roots kind of business. The first function is not equal to 0 anywhere in that interval. Okay? So that's it. Those are the conditions. Just as long as all those functions are continuous and the first function is not equal to 0, then we're absolutely guaranteed a unique solution. A solution exists and the solution is unique. So I was trying to look at the kinds of problems that they gave you in the homework, and it's not very interesting, but we can take a look at some of them and see how it relates to the existence and uniqueness. So homework set number 4.1. Oh, I should do the student view. So we could take a look at the first two problems. The first problem you guys should be able to do. In fact, you had something like this on a test, didn't you? I don't need to do this, do I? All right. So we have a problem here where we're given a family of solutions. Now, how they get the family of solutions is still something that we're going to explore later on. And this is a second-order differential equation, so we should expect two initial conditions if this was going to be a packaged IVP, initial value problem. And this is supposedly our general solution. And again, our general solution is a two-parameter family with two unknown constants. And if we're going to find a specific solution, a particular solution, then we need to use our initial conditions. So when y is equal to 0, when x is equal to 0, y is equal to 0. So we got 0 is equal to c1 times e to the 0 power plus c2 e to the 0 power, which is just 1. The next one is the derivative, so I need the derivative of this thing. Y prime is equal to just c1 e to the x and negative c2 e to the negative x, which with the second initial condition will give us 7 is equal to c1 e to the 0 minus c2 e to the 0. So we have a system. We got c1 plus c2 equals 0. c1 minus c2 equals 7. You can almost do this in your head, right? When you add the equations, you're going to get, what is it? 2c1 is equal to 7. Divide by 2, so c1 is equal to 7 halves. c2 is equal to negative 7 halves. So those are your solutions, or those are your unknown constants. Now they're known, and now you have one particular solution for this family. Okay? So different values of c will give you the correct solution, but these two specific values of c, c1 and c2, will give you the exact solution for your IVP. And when I say IVP, I mean it's the differential equation with the initial conditions. That's your IVP all put together. Okay? Done? Let's take a look at the next problem. The next problem addresses the existence and uniqueness theorem a little bit more directly. And the existence and uniqueness theorem is kind of based on a particular interval that contains your initial point. And so in this particular problem, they want us to find the largest interval, which would contain, that includes 0, which would contain your unique solution for your IVP. So our IVP is this whole thing. It's the differential equation, and you have two initial conditions. So let's look back at the theorem and try to remember what the conditions are. So if I want to take this, let me rewrite this equation. X minus 3 times y double prime plus 4 times y is equal to x. Now, if I really want to get nitpicky about this and try to identify all the different functions that I have, I would identify this as a sub what? What's a sub n? In this case, this is a second order differential equation, n is equal to 2. So a sub 2 of x is equal to x minus 3. So that means I have a sub 1, a sub 0 functions. What is a sub 1? Now, tricky. The a sub 1 would be the function that would be multiplying with the y prime, right? And the y prime doesn't exist, so that means it must be being multiplied by 0. And a sub 0 is, somebody already said that, it's 4. What's x, or at least in terms of the theorem or the initial setup that we had? G of x is the other side of the differential equation, which we'll call x. What I did was I just wanted to identify all my little functions here, because according to the theorem, I want to check all those little functions to see if they're continuous. And then one more thing, that's one part of the conditions for this theorem. The other part of the conditions for the theorem is that the leading, I don't want to call it coefficient, but it's kind of like the coefficient function is not equal to 0. So, what can you say about these functions? Are these continuous? These are all continuous. On all real numbers. So that's good news already, yeah? Well, y prime isn't here, and so we kind of have to assume that there's a 0 times y prime, and so the thing that's being multiplied with y prime is 0, and that's how this came up to be 0. So it looks like from the first condition that we could probably potentially have minus infinity to infinity as our thing. But it's not, because what's the second condition? Whoops. The second condition is that the leading coefficient function, a sub n, or in this case a sub 2 of x, has to also not be equal to 0, or anything that would make it equal to 0 would go away. So I don't know if I should put a slash here or not, but let's consider when this is equal to 0. That's equal to 0 when x is equal to 3.
So what does that mean?
That means, according to our second part of the conditions, this is not that it's not unique, but if this was part of this, then I can't guarantee that you're going to get a unique condition 1, condition 2. So there's two conditions to check for your existence and uniqueness. And so I have an issue at x is equal to 3. So in my number line, x is equal to 3, I can have my interval to be on the left of 3 or on the right of 3, but I can't have it containing 3. So how do we know which interval we're going to choose to find our largest interval value? You can, well, no, you can't do a union because your solution has to be continuous within some interval, and if it breaks up there, then you just throw away the other side. Yeah, so it's the one with 0, right? So according to your problem here, find the largest interval which includes 0 for which the given condition, the given IVP has a unique solution. So x is equal to 0 is right here, so I would have to choose this interval, not including 3.
So we could choose negative infinity,
comma 3,
3 with the
parentheses. So you don't include 3 because 3 is not a good point. Okay? So then that's your largest interval possible. You can't get any larger than that because you can't get past 3.
So does that mean that there's not like an asymptote?
There's a good chance that there's going to be an asymptote.
What if your initial condition was X or was 3?
They wouldn't give you an initial condition of 3 here because that wouldn't work at all. Then you would have no solution. You're not guaranteed anything. Okay? All right. So that's the existence and uniqueness theorem. It basically guarantees a unique solution if you can satisfy those conditions. Which means that problem that you couldn't do on the test, if we ran it through this thing, it probably would have a unique solution, except you just can't do it by hand. It's like those integrals. You know, there's integrals that you can't integrate, right? But we can get approximations if we give it limits. So kind of like the same thing over here. Sometimes we can't take the differential equation, but if we have an initial condition, then we can approximate using Euler's method, which is apparently a bad way to approximate things. So later on, we'll explore other numerical methods for finding your solutions for your next HBA. Okay, so that's the existence and uniqueness theorem. Let's take a look at boundary value problems, which again I gave you on a test. Huh? I don't know if anybody realized that, but boundary value problem was highlighted in a little box at the end of one of the sections in Chapter 1, so I thought it was fair game. Yeah, I think Taylor polynomials is fair game for Calc 1. So I usually give a Taylor polynomial problem for Calc 1. And then somebody complained. Well, they complained to me, and I think they wrote a bad review in the ratemyprofessors.com saying I was the hardest professor ever, and I was going to be a math major, and now this is all getting recorded, huh? Let's pop. All right, boundary value problems. So what is a boundary value problem? For boundary value problems, we're just going to stick with a second order. And a boundary value problem takes a look at the boundaries, right? Boundary value. Takes a look at the boundaries and tries to see if you can find a solution given a boundary. Instead of initial conditions where they say, okay, the original function at 0 or at somewhere is equal to something, and then the first derivative at the same point is equal to somewhere. What they do instead, let's see if I can get a graphic of an initial condition. So IVP, initial value problem. takes a look at a point here. Let's call it x naught and then y naught. So initial value problem, let's say second order, tells you your starting point, and then it tells you your starting slope. So with a starting point and a starting slope, you should be able to figure out how the rest of your graph is going to go. So that's an initial condition. And remember, the existence and uniqueness theorem applies to the initial condition, initial value problem. So on the other hand, if we take a look at this boundary value problem, BVP, sounds like an underwear, isn't it? Oh, that's BVD. Oh, man, really? Holy smokes. Nothing. Absolutely nothing. I should edit that out. All right, BVP, boundary value problem. The picture of that, well, it would have different, you'd have different scenarios. There's different possibilities here. One possibility, I think the easiest possibility, is this one, where instead of giving you one point, one x value, and then it's going to give you a y value and then the slope value, y prime is your slope here, by the way. It's going to give you an a value and a b value. It's going to give you information about the endpoints and won't necessarily give you any information about the slopes or anything like that. So as long as you have some information about the endpoints, then there's a good chance that I can find a solution that connects those two things. So that's the picture that's involved if you have a differential equation with boundary conditions that tell you something about the boundary of this graph. Now your boundary conditions can also look like any of these combinations of derivatives or original function values. Like the first one can be the derivative of the first at the first point, and then the actual value at the second point at the other boundary. So this would be another type of boundary value. And so there's going to be 4 types of boundary value problems that you could possibly have. It'll be a differential equation subject to one of these conditions. Now, there is no existence or uniqueness theorem for boundary value problems. So the existence and uniqueness theorem only involves initial value problems. Does it say here? Well, this is an initial value problem, IVP. So the existence and uniqueness theorem only applies to the IVP, which means if somebody gives you a boundary value problem, we can't guarantee, even if those conditions are satisfying the A2, A1, A sub 0, and G of x, there's no guarantee that you're going to come up with a solution, and because there's no existence theorem for that. Because there's a possibility that you can't have a solution that would connect these two things and satisfy the differential equation. Not only does it not guarantee a solution, but if you come up with a solution, it's not guaranteed to be unique, which is to say that there might be more than one. There might be 5 solutions. Okay. So we don't have an existence and uniqueness theorem for boundary value problems. Which is why we generally don't study it. So it's introduced here, and we're going to do 1 or 2 problems, but after that, we're going to focus on IVPs. Not that it's not worth studying, because it still can be, it's applied and it's in engineering and circuits and stuff like that, but we're not going to worry about that. Okay, let's see if there are any questions on the homework that apply to boundary value problems. You guys can work that out. Okay. Let's go on to homogeneous equations. Wait, we did homogeneous already, didn't we? Yeah. So there's an unfortunate overuse of a term here. This homogeneous is different from the homogeneous that we learned earlier. So you just have to work that out, that when you're talking about a homogeneous first order differential equation, then you're dealing with homogeneous functions. When we're dealing with higher order differential equations and you see the word homogeneous, then this is what you should be looking at. So no, not necessarily. Yeah. But in this case, we're going to focus on linear differential equations. All right. So a linear nth order differential equation is homogeneous if the g of x is equal to 0. You know that function that's not being multiplied by any of the y's or y primes or anything like that? If that function on the other side is 0, then it's called homogeneous. If you have something that's not 0, I mean x minus 3 is not 0. It might equal to 0 when x is equal to 3, but it's not identically 0. That means that you're not looking at the 0 function. Then it's non-homogeneous. So it turns out that solving for homogeneous equations is easier, and not only easier, but it's actually the step that we take to solve for the non-homogeneous equations. So our first focus will be dealing with homogeneous differential equations. Okay. Basically, homogeneous is 0, and non-homogeneous is a non-zero function. Okay? Questions about homogeneous, that term? Homogeneous? Okay. So along the way, they also start to describe and define linear operators. And they start off with what's called a differential operator. And this is more notation at this point. And depending on what you plan to study or how we're going to study the next couple of sections, this might be important. In general, I don't really dwell on this idea too much, but I think it's a good piece of notation to understand in case I sometimes use it in class. So you know how we take dy dx and we say ddx to take the derivative of something? I say that a lot. I say let's ddx it, which means to take the derivative of it. But the capital D is the notation for the derivative. And what they decide to do here is they take the d of a function, and that means to take the derivative, right? But now what they did is they string a bunch of things, attach a bunch of things to it, and they say this is a linear operator. or a differential operator. And notice this notation, right? It's not a typo that you don't see any y's in there. What? That's the point. The point is that you don't see any y's in there because you can leave y on the outside, and then you can multiply? No, multiply is not the word. You can use this as an operator to apply to y, to apply to a function. And what happens there is that in some cases it would be easier to deal with this if it was if we could just deal with the differential, with the linear operator by itself. Right? So if I had a differential equation that looked like this, for example, then I can I can pretend to extract the coefficients and then the derivatives, the number of derivatives, and then I can just say I'll apply that to y. I don't know if that makes sense. I might not care. But let me see if I could try to explain it a slightly different way. What if my linear operator looked like this? It'll be x d to the fourth minus ln x d to the second plus 7. So let's say this is my linear operator. So what the linear operator does is it would act on a function. It would be applied to a function. I'll just say Ly. Now initially, how that might look like is x d4 minus ln x d2 d squared plus 7 applied to y. And then you would kind of instinctively think about the distribution and distribute the y, right? It's maybe okay. You can think about that way. So it would be x d4 y minus ln x d squared y plus 7y. Well, that's what Ly is equal to. I didn't set it equal to anything else on the other side. Well, maybe we can. Let's say Ly is equal to 0. So then this whole thing is equal to 0. Now, if that looks like a differential equation already, then we're all good. If it doesn't, then we'll take one more step and say d4th y is the fourth derivative of y. So we can rewrite this as x times the fourth derivative of y minus ln x times the second derivative of y plus 7y is equal to 0. So now I have a fourth order differential equation, homogeneous. Well, what I did was I just wrote this and said that this is technically my linear operator. So if I want to dress it up a little bit differently, I could say L f of x, where I can apply it to f of x, whatever f of x is. That does the same thing, just y. Okay? So, well, all this would do at this point is provide us with with another notation. Now, how we would use it, well, we'll see later on. Okay? So that's a differential operator. And like I said, I might not use it. It depends. There's this way of approaching non-homogeneous differential equations where this would be useful, or we can do something a little bit different. We'll see how it works out. So that's your differential operator. So the differential operator is a linear operator. And again, more stuff that may or may not be important for us. I suppose if you're taking linear algebra, you should see kind of the connections here. So the above differential operator is an example of a linear operator. A linear operator on functions is one that satisfies the following. It satisfies basically addition and scalar multiplication of things. Where if we were to take a linear operator or something that we're adding, it's the same thing as taking the linear operator of the two things and add it after you do something to it. And then if there's a constant inside of what we're adding, or constant inside of the function, then it's the same thing as taking the constant out. Is there another operator that sounds really, really familiar that does that? You understand what I'm talking about? Is there another something that we do in calculus that does that? No. Well, let me show you what I'm talking about. If I was to take the derivative is a linear operator, clearly. We just said that in the previous page, except we call it the D operator now instead of the derivative, but it's the same thing. So if I have 3 times, I don't know, I need a function, sine x plus 7 times ln x. If you were to take the derivative of this, you would break this apart, right? Now, you probably don't think about this in your head, but you would say, oh, I could take the 3 out. Well, first, I can split this up to 2 different things that I would take the derivative of separately. And then when I take the derivative of the first one, I can take the 3 out, and then just take the derivative of sine x by itself. And then I can do the same thing, take the 7 out, and take the derivative ln x by itself. So that's that property that allows you to do that is linearity. This is a linear operator. Now let me ask you again, do you know of another operator that does this? What? Integrals. Integrals. You guys remember integrals, don't you? If you were to take the integral of 3 sine x plus 7 ln x dx, you wouldn't try to bunch all that together and do some u substitution that combines x and ln x, unless they're being multiplied, in which case you're pretty much screwed. If you're adding and subtracting, then you would want to split that up to 2 integrals. And what's the first thing you think of when you have a constant inside of the integral? Take it out, right? So that's exactly what is happening. 3 integral of sine x dx plus 7 integral of ln x dx. It's a linear operator. Derivatives and integrals are examples of linear operators. Are there other linear operators? I can think of another linear operator that doesn't necessarily work on functions, but works on something else. You guys have heard of matrices, haven't you? So this idea of the derivative of the integral are examples of linear operators that work on functions. And so if I have a combination of functions with scalars in addition, and then I take the linear operator of that, then I can peel out the scalar and then split up the addition. Well, it turns out for matrices, I can do matrices are linear operators on vectors. So if I have vectors, I'll call it V1 and V2, but matrix A, let's say the matrix is, let's call it M. So M applied to alpha V1 plus beta V2 is going to be the same thing as alpha times M applied to V1 plus beta times M applied to V2. Now maybe this notation will make a little bit more sense. For those people that are taking linear algebra right now, this notation might make a little bit more sense in a few weeks, if it doesn't already. I hope if it does, then that's great. But we haven't talked about matrix multiplication or applying to vectors yet. Well, that's the thing, is that when you apply a matrix to something, we can think about it as a multiplication. But what kind of times is it? There's matrix multiplication, there's scalar multiplication, there's scalar times vector, scalar times matrix. But a matrix times a vector, it's really called a matrix applied to a vector. All right, but matrices are another example, is one of the biggest examples of linear operators. In fact, there's a whole course on that called linear algebra. Okay, so that just kind of gives us an idea of linearity and what does it mean to be linear and stuff like that. And we talked about linear in this class, haven't we? Have we had linear? Oh yeah, the differential equations can be linear or nonlinear. So we kind of got an idea of what linear means, right? So that's good, because we're going to explore the idea of what's called linear independent. All right. Another piece of theory that will be important for us as we study higher order differential equations is the idea of superposition. It's a simple idea. It looks complicated and stuff, but it's really not that big of a deal. The superposition principle says that if you know that you have these solutions, y1, y2, and et cetera, yk for a differential equation, then any linear combination of those solutions is also going to be a solution. What? Does that make sense? Yeah. Well, let me take a look at another example back here. The homework problem that we were doing. Y double prime minus y is equal to 0. Let's take a look at that. we have y double prime minus y is equal to 0 is our differential equation. Let's start off with thinking about how we can solve for that differential equation. Or let's not talk about how we can solve for that differential equation. Let's just say I know for some reason that y equals e to the x is a solution to that differential equation. Okay? So let me check that. Is that really true? I would need the second derivative, so y prime and y double prime are all equal to e to the x. And so if I put that in here, e to the x, that's the y prime, or y double prime, minus e to the x. And that's equal to 0. So yes, this is a solution. So that's verified that it's a solution. What if somebody else told you that y equals e to the negative x is also a solution? Let's check that. Let's check that. So we need y double prime. Y prime is negative e to the negative x, and y double prime is positive e to the negative x. So if I put that into the differential equation, y double prime minus y, that's also equal to 0. So they're both solutions, right? So I got one solution, I got another solution. So what this is saying is that if I come up with a linear combination of those two functions, and a linear combination means you just multiply it by a number and add it to another function that you would have multiplied by another number. And so y is equal to some constant e to the x plus another constant times e to the negative x is also a solution. We kind of already, we didn't show that it was a solution in the problem, but we actually found a particular solution from an initial condition. So
Does this also follow where your a n not to 0?
say it again.
Does it follow like the same?
Where an is not equal to 0? Yeah, well, this is part of the existence of unique theorem. Actually, that doesn't cover that yet because there's no initial conditions here. So this is just general. This is before that. But what this does is allows us to find solutions one by one and then put it together just by making it as a linear combination. Okay? Should we do another one? Let's see if we could do another one. I'd have to make up another problem in my head. Let's see. Y double prime plus y equals 0. Yeah, now I'm not sure. E to the x, is e to the x a solution to this? Now, if I take the derivative twice, I get e to the x plus e to the x, and that's not equal to 0. Is sine x the solution to this? How did you know that? Oh, it was a homework? Oh, good. So y prime is cosine x, and y double prime is negative sine x. So negative sine x plus sine x equals 0. So this is a solution. I wonder if we can find another solution. Yeah. Cosine? Let's try cosine. y equals cosine x. So the first derivative is negative sine x. The second derivative is negative cosine x. So negative cosine x plus cosine x is equal to 0. Yes, that works too. What does that mean? Something like that. But what does that mean about these two solutions in the differential equation?
Have a linear combination of the
Yep. So if you put a linear combination of the sine x and the cosine x solutions that we found, then this is also a solution to your differential equation. That's a superposition principle. Any questions?
There's a third.
No. That's what they make you think. They make you think that let's guess something. And while there is some value in trying to guess for your solution, there is actually a method for doing this. All right. So we got the superposition principle. Is that cool? So if you can find a solution, we can find another solution, put those two solutions together. What they're not quite telling you here is that, can we find another solution, I wonder? Negative sine? Negative cosine? They're just scalar multiples, right? So, I mean, C1 and C2 are negatives, and they're kind of counted. So we can ignore that, although this was a good answer. Can we find more solutions that aren't sines or cosines? You think? Yes? Okay, let's think about this. Back in chapter 1, we talked about the family of solutions that we would get, right? And for the first order differential equation, we would get a one-parameter family of solutions. For the second order differential equation, we would get a two-parameter differential equations, etc. This is a second order differential equation, and we have a two-parameter family of solutions. So if we were to come up with some more solutions that's different from sines or cosines, then that would be a third parameter family of solutions. So that would be too much. Say it again. So the answer to this is no. We will have no more solutions that we can find unless they're somehow related to sines and cosines. Okay? All right. Maybe that's jumping ahead a little bit, but let's take a look at where we jump to.
But how do you find how many elements?
You would order, right? Okay. So, where are we? You know what corollary is? What's a corollary? In math, a theorem is something big that you prove. Something like, wow, the fundamental theorem of calculus is some big thing that we prove. A lemma is something that we would use in a big theorem, but it's kind of smaller. And so it would be less work to prove it, But if we prove this lemma, then that's going to greatly help us prove the theorem. A corollary is on the other side of that. Once you have this theorem, and you've proven this theorem, corollaries are things that would follow those theorems. And it was one of those things where it would follow so obviously that people don't usually prove corollaries. Because it's obvious. Let's see if this is obvious. Corollary. If y1 is a solution, then so is c1 times y1. Is that obvious? Because it's linear, and the c1 can go outside of that linear, and then it's equal to 0 anyways, because this is really a theorem for homogeneous differential equations. So, yes. The trivial solution, y is equal to 0, is always a solution to a homogeneous differential equation. So if you put 0 in for y, the derivative of 0 is 0 and all that stuff, and then the right-hand side is equal to 0 anyways. So is that painfully obvious? If it's not obvious, write it out. So corollaries, these are things that would follow from that statement about the superposition. All right. Now, in that last example, we came up with the sine and cosine functions as solutions, and I say, can you find me another solution? And somebody yelled in the back, negative sine, negative cosine. And I said, they're the same thing. They're the same thing because negative sine and sine are linearly dependent. And positive cosine and negative cosine are also linearly dependent. So this idea of dependent and independent, I think, is something that we need to discuss. And here is a definition, and then we'll find a way to figure out if things are linearly independent or if they're linearly dependent. So a set of functions is said to be linearly independent if there exist constants that are not all equal to 0, such that this linear combination of those functions is going to end up being equal to 0. You got to love this in math. If it's not linearly dependent, then it is said to be linearly independent. Feels like a corollary. I'm not using that word right there. Okay, so if f1 was equal to sine x and f2 was equal to negative sine x, we can ask ourselves, are these two linearly independent? I already said they were. But let's see if we can prove it using this definition. So if I had c1 times sine x plus c2 times negative sine x, can I find a value for c1 and c2 that would make this equal to 0? I can use c1 is equal to 1 and c2 is equal to 1. I can use c1 is equal to 5, c2 is equal to 5. I can use a bunch of things where c1 is equal to c2. Example, c1 is equal to 1, c2 is equal to 1. Then they would be non-zero constants that would make this whole thing equal to 0. So this is linearly dependent. On the other hand, if we take a look at the original two functions that we came up with, the sine and the cosine, c1 times sine x plus c2 times cosine x equal to 0. Can I find c1 and c2 that would make this equal to 0? No. They'd have to be 0. So the only way to make this 0, only possibility, if C1 equals 0 and C2 equals 0. So that doesn't happen. So it's not linearly independent. So it must be linearly dependent. Oh, thanks. Okay. So that's one way to check for independence. And if you're taking linear algebra, we're going to get to that really soon. But in differential equations, when we're looking at functions and linear independence of functions, this is not usually an easy way to approach this. So we need another method to try to check for linear independence. And the way that we're going to check for linear independence is through the Wronskian. It's a cool name, huh? It's like a Jacobian. It's the Wronskian. We're going to Wronskian it. Whatever that means. So, we obviously don't have time for an example, but next time we're going to pick up by studying linear independence of functions using the Wronskian, and then hopefully we'll be able to start finding these functions through whatever Francisco was asking earlier. How do you find it? All right, see you guys next time. Have a good weekend.